Welcome to this explainer. Today, we're diving into something that feels, honestly, a bit like modern alchemy. We are looking at this rigorously engineered blueprint that takes hazardous, regional municipal waste and literally transforms it into clean industrial energy. It's an absolutely fascinating process.
To start, I want you to picture this: 120 megapascals. Just imagine the sheer massive force of that localized pressure. Well, that is the exact mechanical threshold this engineering solution uses to literally compress a deadly environmental crisis into a sustainable, high-density asset.
Right here on the screen, we've got our master blueprint. If you look on the left, we start with a very real environmental challenge of toxic smog and raw leaf waste. But as we trace this process through 5 phases, all the way from collection to compaction, we end up with a perfectly clean, near-zero sulfur industrial biofuel that is completely ready for factory boilers. It's just a beautifully elegant visual narrative of the solution we're going to unpack today.
Here is our roadmap. 1. The winter smog crisis. 2. Re-engineering foliage waste. 3. The science of compaction. 4. Biofuel versus industrial coal. And finally, 5. A closed-loop solution.
All right, let's kick things off with Section 1, the winter smog crisis, Punjab's dual villains.
So there are 2 main culprits driving this massive localized crisis in the Punjab region. On the top path, you've got municipal open-air leaf disposal. Basically, burning these leaves in oxygen-starved environments pumps out black carbon and volatile organic compounds. Then, on the bottom path, you have small to medium industrial facilities burning indigenous subbituminous coal, and that coal is packed with 2.5 to 4.5% sulfur, which just dumps massive amounts of gaseous SO2 and fly ash right into the air.
But here's the real kicker. What happens when those 2 emission pathways actually meet? Well, they get caught by something called thermal inversion. You can think of this as a micrometeorological trap that locks all that toxic smog right down in the breathing zone. We're talking about hazardous PM 2.5 concentrations exceeding 350 micrograms per cubic meter. It literally stalls the regional economy and just completely overwhelms the local healthcare systems.
Moving right along to Section 2, Re-engineering foliage waste, the master plan.
So, with a crisis of this magnitude, how do we eliminate both the municipal leaf waste and the industrial coal dependency at the exact same time? We have to flip the script and move from a liability to an asset. Starting on the left, you have raw foliage waste, right? It's a wet, low-density liability full of irregular particles. But by applying that 120 megapascals of continuous thermomechanical densification, along with 90 degrees Celsius of dye heat, the engineers trigger what's known as the Walker-Heckel dynamic. This transforms a loose, soggy pile of leaves into a highly standardized, dense, solid biofuel that actually exceeds 1,100 kilograms per cubic meter.
Let's dig into Section 3, the science of compaction, modern alchemy.
How exactly are they pulling off this compaction process? Well, to make sure this biocoal meets strict international protocols, the engineers rely on a very specific 5-phase empirical framework. It goes from initial sourcing and multi-sieve milling, through slurry matrix blending, into the heavy dye compaction and curing, and then finishes up with standardized durability assays and adiabatic calorimetry testing.
Looking closer at the first 2 phases, the level of meticulous detail is just fascinating. First, raw leaves undergo solar dewaterification for up to 72 hours. This drops their moisture from a really soggy 60% down to an optimal 10%. Then, an industrial hammer mill completely pulverizes them into very precise, uniform 3mm particles. Meanwhile, over in the reaction vessel to the right, starch residue from agricultural wastewater is heated up to 85 degrees to create a gelatinized binder. Next, the material is fed into the compression chamber, where that 120 megapascal continuous linear force pushes the biomass through. The extreme shear force is combined with the electrical dye heating, which is kept precisely at 90 degrees Celsius, trigger a glass transition in the natural lignin of the leaves. So the lignin literally melts under all that pressure, acts as an internal binder, and extrudes out the other side as a solid, perfectly uniform briquette.
Now, natural lignin is great, but it's not quite enough on its own. To translate some of the heavier viscoplastic flow jargon from the source material for you, they basically use a secret sauce. They mix in a 10% gelatinized starch matrix that's harvested directly from agri-industry wastewater. And this acts as an incredibly strong, structural organic superglue.
And if you're wondering why that starch is so absolutely critical, just take a look at this chart. Without the binder, that's batch A, the shatter resistance is only 74.5%, which means those briquettes would just crumble apart during transport. But look over at batch C. Adding just that 10% starch matrix rockets the shatter resistance all the way up to 97.8%. It transforms the briquette into a superior, highly hydrophobic industrial fuel that easily survives long-distance logistics.
Which brings us to Section 4, Biofuel versus Industrial Coal, the ultimate face-off.
Okay, so we know the impressive mechanics of how it's made, but how does this engineered leaf block actually stack up against the highly toxic status quo of indigenous Pakistani coal? Let's check out the operational footprint.
Cutting through the jargon, this simple table really says it all. Check out the bottom row. The leaf briquette generates a gross calorific value of 3,900 to 4,250 kilocalories per kilogram. That means it successfully matches roughly 85 to 90% of the coal's thermal output. But then look at the top row. It drastically slashes the ash content from up to 38% all the way down to just 5 to 8%. And that is huge because it prevents the convective slagging that normally ruins boiler tubes.
But here is the absolute game changer for regional air quality. Because the leaf briquette drops elemental sulfur from a dangerous 4.5% down to less than 0.05%, swapping out the coal results in a massive, greater than 95% reduction in sulfur dioxide emissions. I mean, it virtually eliminates the primary chemical precursor to winter smog.
Finally, let's look at Section 5, a closed-loop solution, macroeconomic impact.
Let's zoom out for a second and see how this brilliant piece of laboratory engineering becomes a functioning, large-scale reality. What we have here is a perfect closed-loop supply chain. If you follow the cycle, it takes a municipal sanitation nightmare in Node 1, so dead leaves and wastewater starch, cycles it through localized densification hubs in Node 2, feeds the massive energy demands of local SME industries in Node 3, and results in clean air and atmospheric recovery in Node 4. It completely breaks that thermal inversion cycle we talked about.
At the end of the day, this is about way more than just clever chemistry or saving the environment. It's a highly profitable macroeconomic model. It creates localized processing jobs and, maybe most importantly for the industry, by standardizing a domestic localized fuel source, it completely insulates small and medium manufacturers from the crazy volatility of global fossil fuel pricing, all while systematically cleaning the local atmosphere.
This whole Blue Point is really just a masterclass in elegant circular engineering. It takes something we literally sweep into the gutter and burn as trash and turns it into the very thing powering our industries. Which leaves us with a fascinating final thought. If we can engineer dead autumn leaves to successfully replace toxic industrial coal, what other overlooked urban waste streams possess this kind of hidden world-changing potential? Thank you so much for joining me for this explainer. Keep questioning and keep looking for the assets hidden in the liabilities.